Assalamualaikum, my name is Muhammad Fahim bin Muhammad Azim. For this lab to robotics, I am doing this demonstration myself. The objective of this experiment are to study the kinematic model of a differential drive mobile robot and to understand the difference between open loop and closed loop control. Also to implement P and PID controller in simulating and to analyze how controller parameters affect the robot performance and tracking error. The robot used in this lab is the Pointer DX differential drive mobile robot. The parameters are position x and y and orientation phi. The input are linear velocity u and angular velocity omega. I use MATLAB Simulating as the tool. The advantages is it has a user-friendly interface and we can see the robot respond in real time through the scope. The disadvantage is the result is on the simulation and may be different from the real hardware. For the setup, I use two simulating models. The first model is for the open loop and the second model is closed loop control. The initial condition for the robot is set as x equal to 0, y equal to 0 and phi equal to 0 for all the tests. Now open the simulink and then open the link given in procedure for the part A. For the procedure, first set the initial condition, the x, y and theta 0, 0, 0 and then run the file to observe the output scope. Select two additional z for the final position for the x and between 10 to 10 and y equal to 0. To find the final position, we need to set up the step which is for the input. So we choose 0.5 and the desired position x equal to 2 and y equal to 0. We just run the simulation and see the output. So the output show the desired position which is x equal to 2 and y equal to 0, and also we can see the center time is equal to 4. Okay, for the next part, open the MATLAB and then just open the file have been given in the part B link. First of all, after open, we rearrange and connect all the closed loop control. First, we connect position error world frame to position error robot frame and position error robot frame to the controller, and then the controller we connect to the mobile robot kinematics. So next we need to choose the desired position for the x and y between 10 until 10. So we choose desired position for the x is 2 and y is 0. And then let's click the controller block diagram and change the KPU and KPW based on the table 1. First we are choosing KPU is 0.5 and KPW is 0.5. Okay, next just run the simulation and then open the output. We need to record the output of graph and then do the observation for sample 2. After that, just continue the next KPU and KPW value. Using the same desired position x and y between 10 until 10, just repeat the step 1 but with the different PID control by tuning that so the satisfactory the output graph, and then just run the simulation and then click the output and record the output graph. Okay, as a result, first for the part A, we target x and y to 0 with u equal to 0.5. From the scope, x increase linearly but there's a steady state error. Y and phi stay at 0. Second case, target at negative 2, 0 with u equal to negative 0.5. The response is mirror of the first case. Third case, target at 6, 0 with u equal to 1. The robot moves faster but steady state error still exists. From part A, without feedback, the robot cannot correct its error. The movement fully depends on the input given. Okay, for the part B, I test with KP equal to 0.5, 1 and 12 at target to 0. When KP is equal to 0.5, the robot moves slowly and still has error. When KP equal to 1, the response becomes faster and better. But when KP equal to 12, the robot oscillate and become unstable. I also test target negative 6, 7 with KP equal to 1. The robot can reach the diagonal position but with some overshoot. For the part B, P controller improve performance compared to open loop, but high KP can cause instability. Okay, lastly for the part C, we use controller to improve the steady state error from part B. First, I use the default PID value P equal to 1, I equal to 0, D equal to 0. The robot reach the target but still has some error and the response is not very smooth. After I tune the PID by increasing P and adding some small I and D value, the robot reached the target faster and more stable. the steady state error is reduced. I also test at target -7 using the tuned PID. The performance is clearly better than using only P controller. From BATC, the PID controller gave the best result after proper tuning. The term I in the PID term is reduce steady state error, and the T term improve stability. In overall, open loop control has no feedback, so error cannot be corrected. P control improve the response but need to correct KP value. PID control give the best performance after tuning. This is the end of Lab 2 demonstration. Thank you.